Hello everyone, my name is Jón. I'm the head of insurance for NTI, and with me today is Hulda, CEO of NTI. In the light of the ongoing volcanic activity on the Reykjanes Peninsula, we thought it was important to give you more insight into the situation, focusing on the hazard on the entire Reykjanes Peninsula, and as well give you opportunity to learn more about the prevention measures which have been successfully used in the area around the village Grindavík. Today we have two specialists which will give presentations. First we will have Professor Magnús Tumi Guðmundsson, a geophysicist at the University of Iceland. He will present and discuss the hazard on the peninsula. And then we will have Hörn Hrafnsdóttir, a civil engineer and a specialist in fluid mechanism, and she will discuss the prevention measures which have been used in the area around Grindavík. So to make it short, I will kindly ask Professor Magnús to take the floor.
Yes, good morning or good afternoon, everybody. I'm going to talk about the volcanic hazards, maybe a little bit about the risks, but also about the vulnerability to lava flows and other risk factors on the Reykjanes Peninsula and the present situation. I would like to acknowledge the work and contribution of my colleague Magnús at ISOR, who has worked on mapping the lava flows there for decades. I'm going to talk about the volcanic activity and the related hazards on the Reykjanes Peninsula. I'm going to go over the geology and the characteristics of the peninsula, go over the activity since 2021, and then importantly the lessons we have from previous activity. And then what to expect during the present episode of unrest, and the likely behavior of the activity on the peninsula during this volcanic periods that is sort of starting, and the timescales of things, and then vulnerability of infrastructure and inhabited areas. Here we have an air photo of the Reykjanes Peninsula and the sort of southwest corner of Iceland. You see the population centers are marked out there. We have the biggest one is the Reykjavík, which is 140,000 people living here in the capital. And then there is a town of Kópavogur, Garðabær and Hafnarfjörður, a total of 240,000 people. And then we have the towns of Reykjanesbær, Vogar, and Grindavík, importantly, which really stands out as the most exposed, and then also the town of Þorlákshöfn. Now, here we have the geological map of the peninsula. It's rather colorful and may look chaotic to people, so but it shows the very important details here. You see the white dotted line. This is approximately the plate boundary between the North American plate that is going towards east, west, northwest, and the erosion plate that is going to the east, southeast. And they are moving on average 9 millimeters per year, so the total spreading rate is 18 millimeters. And the volcanic activity is due to sort of filling of these voids that are gradually built up over time, and this happens in rifting events that are spread over the peninsula, and they are not very big compared to other volcanic activity in Iceland. The total magma erupted on the peninsula is relatively small compared to other places. The importance of these events is its proximity to towns and infrastructure. And here, if we look at you see this, the colors there of the lavas, the bluish to pinkish colors, and they are gradually younger with the more sort of the brighter the color becomes. The oldest lavas are 14,000 years old, and this is meant, Iceland is all formed more or less as lava flows, but we are talking about since the end of the last glaciation, because Iceland was ice covered until 15,000 years ago. And importantly, you see that the northwest end of the peninsula here is older rocks. And also this area is all older rocks. Then we have lava. And the older lavas extend further, and that is because there was more volcanic activity once the glacier that covered Iceland for best part of 100,000 years, when it disappeared, there was increased volcanic activity. That has subsided now. And here we have the population centers and on what type of land they are built. And what we see here, the Reykjavík area is mostly built on older rock. Not very old, but much older than, well, there has been no volcanic activity there for a long time, and it's outside the active volcanic zone. Then we have the Reykjanes and importantly the Keflavík International Airport. They are outside this area as well. So really those two that are close to the active areas, and Grindavík stands out as being very close. There is also this town of Thorlákshöfn, which is on lava formed 5,000 years ago. Now, volcano-related hazards. What causes possible or damage to infrastructure and buildings? Well, and this is, I'm talking generally now, large explosive eruptions, caldera collapse, these really big events, pyroclastic flows that can destroy everything, lava flows that work locally but they destroy everything that they flow over, faulting and tectonic movements that can cause, with earthquakes, that can cause damage, and then eruption in glaciers caused by floods. So what stands out on the peninsula? There are no large explosive eruptions, just not part of the activity there. Caldera collapses don't happen. We don't have that sort of systems there. Pyroclastic flows, no pyroclastic flows. But we have lava flows. That's the main hazard on the peninsula. And then faulting and tectonic movements, but they are more local, and it's really the town of Grindavík that stands out. And there are no glaciers and no water floods or anything like that that can happen there. Now, to the present activity, the most recent eruptions, this is the Sundhnúkar fissure. It has a very impressive beginning phase that lasts a few hours, where we have extremely high or very high flow rates, but then it drops very fast, and then it may linger on for some time. And it's this beginning phase that is so important to contain, and that it doesn't flow over important infrastructure, but Hörn will come to that later. And you see this picture here with the town of Grindavík, close to here on, this is in January, and then we have this very impressive beginning of the eruption in May, and importantly we see here one of the barriers that has been built that have proved successful so far. Now, the volcanic history. If you look at the last 4,000 years, we have 3 events, and they have been reasonably well documented. There are similar events before, but they are very buried, so the detail is not as well revealed. But we have maybe 4 to 6 centuries of occasional with eruptions, not continuously, but when eruptions happen, and then maybe 600 to 700 years or 800 years of no activity. And you see here, and it's one of the systems active at the time, and there are 6 systems outlined here. And a new period started in 2021. And what do these previous periods tell us? The last 2 are outlined here. This is the one 1900 to 2500 years ago. And you see these pinkish colors. These are the lava flows that were formed. And this is the latest period from 780 to 1240 at the present, in the present era. And you see there are these different lava flows. It looks slightly bigger than the previous one, but it's difficult to say whether it was any bigger. It was very, very similar in magnitude. And if you look at the first episode of the last volcanic period, and that was Brennisteinsfjöll Krýsuvík, that formed these deep purple lavas. And this was around 800 AD. Then in the period 950 to 1000, it was probably not continuous. It was not continuous activity, but it sort of spread out over this period. Then these lavas were formed, and this was the largest episode, producing 0.75 cubic kilometers. Then the third one, and then 150 years passed. Nothing happened. And then we had the third episode from 1151 to 1188. Here we have more detail because there are written sources. And that formed lavas that flowed into the sea here on both sides, not at the same time. But this is something that happens. And then the final one from 1210 to 1240 AD, Reykjanes Svartsengi. And that's close to the area that is now active. And that formed these patches of lava, but there were also small, moderate-sized explosive eruptions here because of phreatomagmatic activity here on the coast. Formed a last layer that was 1 to 5 centimeters thick on the peninsula. These sort of events have no really relevance because they just are not part of, they don't cause any damage to infrastructure or buildings. It's the lavas that count. So in summary, for the last period, there were 4 episodes of activity. Also want to point out, if you look at the last 15,000 years, there are a few considerably larger lavas that were formed, but and they were shields mostly built, caused by the decompression. When the glacier goes, then volcanic activity picks up, and then it sort of dies down, but there have been no lavas of that magnitude over the last 5,000 years, but we cannot rule out that may happen, but it's not likely. And here are just summary here of the numbers. This was something like 2.1 cubic kilometers of lava. This is similar in four and a half centuries. This is similar to sort of 30% of what is produced in Iceland over 1 century. So it's not a very big part of the activity. And here, very importantly, we look at the time scale, the episodes with eruptions in the past. They were probably considerably shorter, but they are at least something like 30 to 40 years, and with intervals with no activity over 120, 150 years. And then this one was probably more sliced together, but a much smaller period. So you see, on the peninsula, we should not, the activity we've seen now will not continue like this for decades or anything. There will be long intervals in between. And here we have the status of the current episode of activity since 2021 compared to the previous episodes in the volcanic period of 780 to 1240. And this is what has been erupted, something like 0.335 cubic kilometers of lava has been formed since 2021. And this is becoming close to or similar to what was formed in episodes 1 and 3 in the previous events. But 2/3 of what we expect seems to be the average, and just under half of what is produced in the biggest one. So if this continues at the current rate, which is quite active, we will see the volume reach in this episode at the end of this year. The mean of these 4 episodes will be reached sometimes in a year or so, if it continues continuously. But let's say if it goes to this, then this will be finished in 2 or 3 years. But there may also be gaps with total duration of episode longer, and that is what applies to at least both these, that they were punctuated. So it's likely that we've already seen something like 50% or more of what will be produced in this episode, so since already erupted. And here we see the lavas formed in the current episode, the deep red ones here, and these are the lavas formed in the previous one. And we see that this is approaching similar magnitude as seen in, for example, the first one here, or in every single episode. And so it has the progress has been quite fast, and possibly some of the earlier first episode did not last for 40 years or something, and if they did, then there were probably longer intervals with no eruptions in between. So we will definitely not see this type of activity as we've seen this year continuing for many years or decades. That is not like anything that has happened on the peninsula in the recent past. And look at these, if you look at these boundaries that are shown here, they are the region where volcanic eruptions have happened over the last 15,000 years. And we see here, this is the town of Grindavík, and if we look at at how this spreads out, these are the population centers. And we see that the town of Grindavík stands out. It is basically the volcanic fissures are very close to the town. They're just at the outskirts of town or have in the past. And there is no other population center or town that is anything as similar to exposure to lava. And it has to be said that, for example, here in this region, this area here has no lava has reached the coast here for 15,000 years, and there is a depression here that will engulf a lot of lava before lava, for example, managed to reach the road to the airport. So that is really not likely compared to the looking at the previous history. So we do have, so the town of Grindavík stands out. It is very exposed to lavas. There is a fissure swarm that runs through it, and the damage that has happened there has not to do with lava, it has to do with movement on these fissures. These towns here don't stand there, and there is really not, so they are very different situation from Grindavík. It really stands out. So, to summarize, the lava flows are the main threat to infrastructural buildings on the Reykjanes Peninsula. Tectonic movements can cause damage, but the hazard is much less elsewhere than in Grindavík, because they are much further away from the fissures. Most towns are located outside the areas where there is substantial likelihood of lava inundation. However, the southern margin of the town of Hafnarfjörður is exposed to lava inundation, but it's currently much further away from possible volcanic fissures than Grindavík. And if activity, and when it picks up there, it's probably something like in the next, after 100, 150 years, looking at the previous behavior. The lava barriers have been effective so far. Over 50% of the lava erupted is probably already there in the current episode. The current episode may continue as it has done since November 2023 and last for several months, or continue in an intermittent fashion for some years. We cannot tell. And it's likely, when the current episode is finished, that volcanic activity on the peninsula may stop for several decades. Thank you.
Hello, everyone. Excuse me. Hello, everyone. I'm going to talk about lava protection barriers for Svartsengi and Grindavík and try to shed some light on why it has worked, so far at least. So let's start where Magnús Tumi finished. So we have the Reykjanes Peninsula. We can see where the lava has been flowing for the last few months. And if you zoom in on the area, we can see the protection barriers we have created and where they are located. And I'm going to focus on Svartsengi and Grindavík, but you can see on the figure that we also have some other barriers outside that area, like here and here, but I'm not going to talk about that specifically. So the question that needed solid answers when we started this work were, where is an eruption likely to take place? Where might the lava flow from such eruption sites? And the key question was basically, can we prevent the lava from flowing where we don't want it to flow? So let's start. So first we needed to have some information about where it might erupt. So scientists in relevant fields were consulted, and the location is based on decades of research, geologic map, interpretations of the behavior of past volcanic activity on the Reykjanes Peninsula, and also newer information like inflation and earthquakes. And we can see here on the right, this is the Eldvarp fissure and this is the Sundhnúkar fissure. These were the locations that were very likely to erupt. So we have lines there, and then we adopt. We maybe start with the whole line, like here in Sundhnúkar fissure, see where the lava might flow, then we change it a little bit, like we take shorter versions of this line where it's not a good location. And then we slide it slightly to the west and slightly to the east to get the worst scenarios, and we design for that. So we needed lava flow modeling and the necessary building and input information, a good terrain model. And then we also need information about the design lava. So we need volume, flow rate, and some lava properties. We started by assuming, using actually 0.13 cubic kilometers for the volume. And this is like a median lava for the Reykjanes Peninsula, I think, during the last episode. And the flow rate we started with was 300 cubic meters per second on average. So to get this volume, we needed like 5 days to get to that volume. But the lava properties were kind of the dark horse. We needed a calibration. So that was quite a work. Additionally, we need to constantly update our information. We need to update the terrain. We have an eruption, the land changes, we need to measure everything and change it. And then we are constructing barriers. We need to change accordingly. And also we test barriers in the terrain, so we have artificial terrain. And also we update the design lava as we learn something new. Like now we have, as we can see here, new design lava scenarios for the Sundhnúkar fissure. And the largest volume so far during one eruption was 0.06 cubic kilometers. And the flow rate is now ranging from, in the beginning, up to 2,500 down to 5 cubic meters per second. And you can see there's a large difference in those numbers from the 300 we started with. So as we go further, we can see how that changes things. So the lava flow models. The models are always approximation of reality. So it's important to know their limitations, their strengths, and their weaknesses. And they may be based on physics, probability, or some empirical formulas and data. The lava flow models we have been using for the design, it's HECRAS, and that is based on physics. and we use that for the design and testing of the barriers. And then we use them also to estimate arrival times of the flow front. And the runs are performed at Verkís, my office. And then we also have Mr. Lavaloba. That is a probabilistic model. We use that for comparative testing of the barriers. And that is run and performed at the Icelandic Met Office. And I think it's very important to point out that we are using two different and very different lava flow models, and they are run by different organizations and different people. So it's like a safe check. And to the right, you can see the difference between the two. So we have similar outcomes very often, but there can be some differences in some instances. And then the calibration of the lava parameters. We started calibrating the lava parameters in the first eruption in Fagradalsfjall in 21. So we got those two sets, the slow and thick lava, which you can see on the figure over here, and then the faster and thinner, which you can see here. And this is during the same eruption. And these sets worked well in the Fagradalsfjall eruptions, the later ones. But when the Sundhnúkar fissure started in December, we saw that it was behaving differently. It was very fast and very thin during the first few hours. So we added parameter set one. And that has worked very well for the first hours of the last eruptions. So the lava models, do they only work in theory or do they work in practice? So let's have a quick look. So a case study, this is Fagradalsfjall, July 2023. And to the left, we can see a comparison of the area covered by the lava. The white line shows the measured actual lava field, and then we have the color filled area that shows the simulated lava field. And I use the colors black to orange to see, how fast it's going. And you can see here the eruption fissures. And to the right, we have a cross-section taken here. And we can see this is the original terrain. This is the lava surface modeled. And then we have a measurement of the lava surface. So we call this a good fit. And this is longitudinal section. We are going from here and all the way down here. And the same, we have the original terrain, we have the simulated lava, and the measured lava. This gave a very good fit for the first 9 days in this case. But after that, the crater broke, there was a part that broke, and the flow went into another direction, so it was more difficult to simulate. So it's very important to know that we cannot get everything by the lava models, so we have to, look into other things and see what's happening in real time. This is another case study. This is the Sundhnúkar fissure. This is from February this year. And this is, the white line shows measured area from the lava. And we can see the simulation here in the color-filled area. And this was actually done during the eruption. So we were doing this during the first few hours. And the measurement is taken much later on. So this gave a very good fit, and there we are using the fast and the thin flowing. But to get the thickness, because the fast and the thin flowing is just, relevant for the first few hours, then it kind of slows down, the fusion rate slows down, and it starts to thicken, and we need to model again. So we use the middle parameter set that I showed you before. So we have the fast and thin, and then we get a good comparison between the thickness of the lava. We can here see the original terrain, and this is the cross-section we are looking at. So we have again the simulated here, we have the measured, and I'll also added the March eruption. So we also have the simulated and the measured lava surface. So the answer is yes to the question we asked previously, but we have to know the limits, and it's essential to analyze the actual lava flow and add that into our design. So the Sundhnjúkar eruption, if you just have a quick look at that, the first 3 eruptions, they had very short duration. First very fast and thin flow for a few hours, then very high effusion rate, and it can flow far in a very short time. But then it was followed by a fast and thin flowing lava for a few more hours, but then the effusion rate was dropping down. And these eruptions were easy to simulate. But then we got the last 3 ones, and we can split them into 2 phases. So we have the first part, which is very similar to the other eruptions, but the effusion rate in the beginning has been ever increasing, and that's where the figure I showed you before, 2,500, that is how it has been growing step by step. But then it's followed by a slower tail, and that can last for weeks. And there we have low effusion rates. We can have ponds, lava ponds forming, like we can see on the figure here, very close to the crater, which you can see here. And lava from these ponds, they can then travel downstream, and they are very thick and slow moving. But they are challenging to simulate. But the good thing is they reach very short distance. They are not going as fast, and they're not going as far. So that's the positive thing about them. So the question is, can we control it? So the first steps taken were a review of prior attempts, both successful and unsuccessful. So we have Heimaey, Mount Etna, and some eruptions in Hawaii. And we gathered lessons learned. And we reviewed possible methods. So we have barriers, cooling, or even bombing. And the results from this is that barriers are the most likely to work, but we can use cooling as a secondary defense, and we have tried that, and it works during certain conditions. The design principles for hydropower dam design were adjusted to lava flow, and we also considered workability based on necessary and or available machinery for the work. And then it was a combined effort of geotechnical engineers and fluid mechanic engineers. We also made test barriers in 2021, 5 in total, and we got very useful results. We got confirmation that we should prioritize diversion barriers over dams, and when I say diversion barriers and dams, I'm talking about, when I say dams, it's a barrier that is constructed to stop the flow, and that's then it has nowhere to go. So obviously it's not as good as diverting it somewhere. And the diversion barriers are good if we try to divert it slowly. So we are trying to be nice to the lava. And then we saw also that slow-moving thick lava can rise well above the top of a barrier without overflowing, and we can see that on a picture here. And then we have the fast and thin flowing lava, and that can flow over a barrier very shortly after it reaches the top. So this is something we used for the design of the barriers, and we can see here how we do it. We do lava simulation both for the thick and the thin flowing lava, and then we choose the height here in between. So this is the fast and thin flowing lava. And this is the thick and slow-moving lava simulation, and we choose elevation in between. And here we can see how it works. This is L1 barrier, and this is the first phase in the May eruption, and this is the second phase that came shortly after. And you can see this is here rising above, and a part of the lava there rolled over and lit the moss. So have they worked? This is just a demo for you to see. This is a simulation we made when we were designing the L7 and L8 barriers. We can see them here. At that point, we had already constructed L6 here, so L6 is included in both slides. But on here, the barriers are not included in the model run, but here they are included, so we can see the difference. This is then a picture from the event in March, and you can see where the lava is flowing few hours into the eruption. It is taking a path towards the town, and then it is diverted along the barrier to the site. And you can see here on this figure that if we didn't have the barrier, it would have chosen this path here into town. And this is, we are looking from this side, and here we can see in green how the lava flowed along the barrier in this case. So it's a measure, the green is a measurement. And this is also from the same eruption. First we had a thin, fast flowing, and here we have also a thick, slow moving part later on. And if you look at L1, some might say that this is an example of a failure, because in this case, we had first fast and thin flowing, then we had slow and thick flowing, and then we had inflation of the latter one. And this huge lava tongue formed here along the barrier. So this is the L1 barrier, and the volume of the lava in this tongue here is about 1.5 million cubic meters, but only 3% of that managed to go over the barrier. So we contained this behind the barrier, while we had some spilling over here. So why has it worked? It's a cooperation between parties on all levels, preparedness and constant awareness, detailed analysis of possible scenarios using lava flow models, solid design of barriers by expert engineers in relevant fields, and we construct before events if needed. We integrate the terrain into the design. We find areas to divert the lava into. We minimize momentum change in the lava flow by using low-angle diversion barriers. Then it's a continuous monitoring and reanalyzing during and between events. Then there is hazard assessment, very important, and evacuation plans, because it's, we have workers working there and eruptions are imminent sometimes. And then, very important, we prioritize all work. So we look at the situation and say, okay, we need to start here because this is more likely to be at risk right now. And as I think we have a few more minutes, possibly, I'm just going to show you this. It's other type of infrastructure that we have been protecting. This is electricity masts, and I hope you can see it here. The dark blue dots are the masts that were there before. And then we made some simulations and said that, okay, we should move them slightly to a safer place and build an earthfill cushion underneath, so we elevate them. But that work takes time. So in the meantime, we erected some barriers just around the masts, and you can see here where they have been erected. And this is after the lava has flowed around it, and it actually rose 2 meters above the top of this barrier. And then another thing, where we have been able to bury pipelines for hot and cold water, they have been active throughout if we have flow going through the pipelines while the lava is flowing over. So they can survive such things, at least in the cases that we have tried. So thank you.
Hello everyone. I would like to thank you for listening to Dr. Magnús Tumi and Hörn Hrafnsdóttir. It has been a pleasure to present this for you, and I hope we will get the option to have some talks about it later on. Thank you very much.